professor in Chemical Engineering Department at LJ Institute of Engineering and Technology. The subject that we are going to continue is mass transfer operations 2. So in last lecture we covered our deviations from ideality. We studied about positive and negative deviation. So moving forward with this chapter, that is distillation. Now our topic for today's lecture is various kinds of methods that are involved in distillation. Okay, what are the different kinds of method? See, starting with flash distillation, then differential distillation, and then fractionation. So talking about flash distillation, it is also called as equilibrium distillation. Now why it is called as equilibrium distillation? Because the vapor and liquid which are leaving the column, right, they are always in equilibrium. Now when it is used when there is large difference of volatility between components. Okay, it means I cannot use it for the components which is having small relative volatility. You have to have the components having large difference in volatility. Second one is differential distillation. Now it is also called as batch distillation. Here also the vapor and liquid are always in equilibrium. Batch distillation means you are carrying out a distillation process in a single batch. It is not a continuous operation. So as you are heating it, your vapors are evaporating, and as vapors are evaporating, they are collected into a condenser. It is condensed and then taken out as a distillate. So as vapor is rising continuously, so vapor and liquid at every instant, at every small instant of time, they are in equilibrium. Hence differential name is there. Okay, at small interval of time your equilibrium conditions are changing here. Last one is fractionation. Now what is fractionation? It is also called as multiple stage distillation. Okay, here in flash distillation, differential distillation, you can take that your process as single stage distillation. Okay, but in fractionation multiple stages are there. Okay, multiple plates are arranged in this column, and so each column behaves as a single stage. Now what is significance of fractionation? It helps to increase the purity of product. Okay, you can see it is a series of multiple stages, right? It is series of multiple stages, and so with each passing of each stage your purity increases. Why? Because it enables more contact between vapor and liquid. Okay, so this was about your methods of distillation. Now studying in deep about flash vaporization. Here is the process diagram of how your flash vaporization method takes place. Okay, first of all, you are taking your feed at some condition, at the initial condition. Okay, the composition of the feed is Z. What is Z here? It is mole fraction of more volatile component at temperature T1, T2. Okay, it is then sent to heater. Now through heater it is sent to a pressure reduction valve and then into the column. In column you can see vapor and liquid are separating. Your vapor has mole fraction of more volatile component as Y. Similarly, your bottom product liquid, it has mole fraction of more volatile component as X. Right? So what we are doing, we are heating it to a new temperature and pressure condition. You can see PF, TF, right? Enthalpy has also been increased. How? By supplying heat. Now this new condition, now this feed having new operating condition, it is sent to a pressure reduction valve. You can see that is a throttle valve. Now because of reduction in pressure, okay, what happens? Flashing occurs. So I can describe my process as, in heater, what does the heater do? It increases the temperature and pressure of the feed to a new level. Then it is sent to throttle valve. What happens in throttle valve? The role of throttle valve is to reduce the pressure. Now it is introduced into the column. What happens in column? Separation of liquid and vapors. Now note down here, liquid and vapors which are separated, right? The mole fraction of more volatile component here now. Suppose in vapor phase the more volatile component mole fraction is 0.7, and in liquid phase the more volatile component composition is 0.5. So that 0.7 and 0.5 are now equilibrium conditions. No more further separation can take place. Okay, here. So let's have a look into working of flash distillation. So yes, this method is also called as equilibrium distillation because vapor and liquid that are leaving the flash column are in equilibrium. It means once equilibrium has been achieved, no more further separation can take place. This method is used when there is large difference in volatilities among the components. So if I've taken my feed solution of A and B, then the difference between volatility of both A and B must be very large. Then and only then you can use this method, right? If boiling point of A is suppose 50 degrees Celsius and boiling point of B is suppose 80 degrees Celsius. So you can see the difference in boiling points. Okay, what does it show? It shows that the difference between the volatility is large. It is not used for multi-component system because relative volatilities of component are not much different. So I can judge that, I can state that this method, flash vaporization method, is used for binary components only. So if I have to distill my multi-component system, then I have to use fractional distillation method. So now moving forward with the material balance part, right? How you will derive the operating line here. So let's start with, let us take an example. My feed is composing of A and B. Okay, I am stating that my A component is more volatile, whereas B is less volatile component. Okay, so F is, what is F? My feed flow rate. It might be kilomole per hour, kg per hour, anything. What is V? V is the distillate. Okay, your vapors are producing on heating. Those vapors you are collecting it, condensing it, and then you are liquefying. On condensing you get a liquid. So what is that? That is your distillate. Okay, it is it is enriched with more volatile component. So what is V? Distillate, rich in more volatile component. L is what? L is the residue which you get in the bottom. Okay, so I can say, now note down here, every calculation, the mole fraction, it is on the basis of more volatile component only, because what is ultimately our goal by carrying out this process? To enrich as much as possible the more volatile component, to separate it. So all the calculations which I am conducting, whatever you conduct in the material balance, right, component balance you do, it is on the basis of more volatile component. So what is Z? Z is my mole fraction of A. A is what? More volatile component in feed. Similarly, Y is my mole fraction of A in distillate, and X is what? Mole fraction of A in residue. Okay, so overall material balance would be what? Feed is equal to liquid, L, that is residue, plus distillate you get, right? Feed is equal to top product plus bottom product, that is your overall balance. Now moving forward with the component balance. So A present in feed, mole frac, okay, amount of A. Here I am talking about amount. It might be in kg per hour, right? So amount of A present in feed is what? Mole flow rate of molar or kilogram, okay, kg weight flow rate. Okay, let's take with the flow rate. Simple. In exam it might be specified that it is kilomole per hour or kg per hour or just simply kilomoles, right? So component balance. Amount of A in the feed is equal to F, that is your flow rate, into mole fraction of A. So that is amount, okay, is equal to amount of A in the residue. Okay, in the residue, whatever A you are getting, plus amount of A in the distillate. Okay, so in distillate, what is it? It is rich in A. Okay, so of course the amount of A would be high in distillate. So V into Y, what is it? It is amount of A what you separated out from your solution, which you are getting in the top product. So that is your component balance. Now further how you will derive it? See, instead of F, now I am substituting L plus V. So I got my final equation. Now solving this equation, L by V is equal to Y minus Z upon Z minus X. This is what? This is equation of your straight line, right? I have to remember this. So see, your L by V is a fraction which you have to learn. Okay, you will see further what is L by V. So how you have to do? This is called as lever arm rule. Okay, lever arm rule. Okay. So what is the numerator? Y minus Z. Right hand side one Y minus the middle one, that is Y minus Z, upon now middle one minus left hand side, Z minus X. So that way you have to remember. Draw a line. Left hand side is your LX, right hand side is your VY, and in the middle is your feed and Z. Okay, so how you have to remember? See, it is a property of line now. L by V is Y minus Z upon Z minus X. So that is your equation of straight line. Now I can also change my this equation, okay, as minus L by V is equal to Z minus Y upon Z minus X. Now, normal, what is the equation of your line? Y is equal to mx plus c, right? So what is m here? M is your slope. Similarly, for this equation of straight line, this is the operating line of flash distillation column. Okay, operating line means how your flash distillation column operates when you change the compositions. Okay, when you change the coordinates, how your equation line is going to change, that is your operating line. So your operating line of flash distillation column is minus L by V is equal to Z minus Y upon Z minus X. So you can see graphically how, using an example, I can see my flash distillation column. F is my 100 mole per second is my feed rate. Okay. So what is Zm? Zm is what? My 0.34. It is mole fraction of more volatile component. Okay. So F into Zm. What is that part? 34. So 34 mole per second is what? A, right? Z into F into Zm. What is that part? That is your amount of A in feed. So that is 34. V is what? 14.3. It means your distillate, vapors that are producing, distillate you will getting. That is 14.3 mole per second. Ym is what? Mole fraction of more volatile component. Okay. From 0.34 it has been enriched. Okay. It has been enriched to 0.58. Means how much I have separated my more volatile component. And in the bottom you can see it is 85.7 mole per second and the mole fraction of more volatile component is 0.3. So you can see on the graphically, slope is minus L by V is equal to minus 6. So you can see the purple line. Okay, the purple line which is there, that is the equation of your operating line for this flash distillation operation. Okay, so Zm line you can see it is near about 0.34. Okay, so that is your feed condition. And in the equilibrium curve where Ym is given in dotted line green color, so that is what? That is up to which you have separated out. Okay, your enrichment of more volatile component which has taken place, that is what? 0.58. And the equilibrium, okay, corresponding the blue line, it is straight line passing through green. Okay, equilibrium. So Ym and Xm, what are these? These are the equilibrium conditions. Means now no more further separation can take place. Okay, 0.5A and 0.3. This is the final condition. Okay, this is the final limit till which you can separate your more volatile component in flash distillation. So now another way of representation, how you represent another way. Okay, we are introducing a new term, that is F. What is F? Fraction of feed vaporized. So note down, F lies between, as it is fraction, so it is between 0 to 1. Okay, 0 to 1, that is your fraction. So if F is feed vaporized, so in vapor form what is it? It is F. So the liquid which is remaining, that is what? 1 minus F. Okay, so I can represent F as V upon F. Okay, F is what? Fraction of feed vaporized. It means vapor produced upon total feed. So that is what? Fraction of feed vaporized. So 1 minus F is what? Remaining liquid. So liquid remaining upon feed, that is what? Liquid phase which is remaining. Now comparing both equations. Okay, what I am doing, I am dividing 1 minus F upon F. So I will get what? L by V. Hence I can write my L by V as 1 minus F upon F. Okay, we can take an example. Suppose F is given as 0.4. I am specifying that my fraction of feed vaporized is what? 0.4. This is my flash column. Suppose I am taking feed as 100 kg. So what would be my vapor? It is 40 kg. So you can see what is how I got 40 kg, right? Fraction of feed vaporized. It means 0.4 into 100. That is my 40 kg vapor. Remaining liquid phase is what? 1 minus F. Hence 60 kg. Okay. Remaining liquid now. So that way you are representing another way. Yes. Now this is how you represent your operating line. Y versus X is there. That is my diagonal and equilibrium condition. So the horizontal line, okay, which is passing through, the slope is what? Minus L by V. What is that line? That is your operating line. This line is your operating line passing through what? Which coordinates? Z, Z and X, Y. Okay. So this is how your operating line is there. Now, at bubble point temperature, vapor formed are very less, but they will be rich in A. It means your mole fraction of A is highest in vapor phase. Now, if I am heating this my mixture at bubble point temperature. What is bubble point temperature? The temperature at which bubble starts to form. Okay, it means your vapors are starting to form, but first what will come out? Of course, the more volatile component will come out. Okay, here the amount of vapors would be very less. Okay, it is just starting to vaporize, so amount is less, but it would be rich. It will be highly rich in what? Your more volatile component. So I can say that fraction of feed vaporized is what? Almost zero, because what? Very limited amount of vapors are forming. So that is almost negligible. Hence F is what? 0 at your bubble point. But your Y, okay, but your mole fraction of more volatile component distillate is what? It is maximum. Okay, it is maximum. It is most pure form. So hence what is the slope here? We saw lastly that slope was what? Minus L by V. So I can say my slope is, again I can represent it how? Minus 1 minus F upon F. But F is 0 here, hence your slope is what? Infinity. Similarly, if I am introducing my feed at dew point temperature, okay, it means your feed is totally vapors. What is at dew point temperature? The temperature at which first dew will form. From dew will form from what? From vapors only. So if I am introducing my feed as whole vapors, okay, only as vapor, then the liquid which will form, the first condensation which will take place, it will of course take place of less volatile component. Okay, so the liquid is rich in B, and the mole fraction of A in liquid is in equilibrium with corresponding vapor phase composition. At dew point condition, what is F? F is again what? Fraction of feed vaporized. Dew point condition means what? My feed is totally in vapor form. Hence F is what? 1. That is all liquid has been vaporized. But it means, what is X gives you? X minimum. It means the mole fraction of A in liquid phase here. Okay, see, every composition is of A only. Okay, more volatile component. So X would be what? X minimum. Because your more volatile component would be high in vapor phase. Now if you are condensing it, first what will condense? Less volatile will condense first. Okay. So the mole fraction of A in liquid would be what? It would be minimum. Hence X is what? X minimum. Now, but the normal flashing operation which we carry out between bubble and dew point. It means the flashing operation, okay, the fraction of feed that is vaporized, it rises between 0 to 1. So you can see this is your dew point condition, okay, and this is your bubble point condition. You can see the conditions for dew point and bubble point, right? At dew point you have what? F equal to 1, and at bubble point you have F equal to 0. Here the Y max, what is Y max? Because you are at bubble point, only your more volatile component is vaporizing. So in Y, in vapor phase, your A would be highest, it would be maximum, okay, hence it is Y max. In dew point you can see in liquid phase, when you are condensing, your less volatile is getting condensed first, okay, B is more here. So A would be what? Minimum. So you can see the slope, F equal to 0 for bubble point, F equal to 1 for dew point. So at dew point, what is the slope? Slope is 0. Whereas for bubble point, what is your slope? Slope is infinity. You can see it is vertical line, right? Vertical line, hence at denominator, your X is what? 0, hence any term upon 0 is what? Infinity, right? In bubble point, you can see maximum amount that can be in vapor phase, that is your what? Mole fraction of A in vapor phase. So the normal flashing operation, how it is done? It is carried out in between 0 to 1. So you can see F equal to 0 is for bubble point, F equal to 1 is for dew point, and your normal flashing operation will take place, that is in between dew point and bubble point. Now equation of straight line was what? Minus L by V is equal to Z minus Y upon Z minus X. So I am changing my equation, okay, I am writing it in form of Y. So what I will get? Y is equal to Z into L by V plus 1 minus L by V by X, okay. Now I am substituting, instead of L by Y I am substituting minus 1 upon F, right. This is, I am substituting in place of L by V. So what I will get? I will get this equation. These both equations are your equation of operating line, okay. These are the equation of straight line, operating line of flash distillation. The important equations which you have to remember for solving the sums related to flash distillation are these two equations in red line. Both the equations in red box are your operating equations in different representation. In exam they can give you F also instead of L and V values. So accordingly you have to choose your equations. So that was for today's lecture. Thank you.